So hello and welcome guys to Accelerated Academy. So we'll be starting a new course as we have already mentioned in the introductory video that we'll be starting off with a series of last minute revision notes and cheat sheets for boards and JE as well. So like in this section we'll try to summarize the entire chapter in a nutshell and highlight all the important points and the most frequently asked questions in exams, okay, like CBSC, ISC or in JE sometimes also. So we have tried to made we have given our best to make this notes and just to summarize the thing in a concise way, and like it's easy for you to revise, and we have only highlighted the important parts and all the relevant parts only. So you will find this in the playlist of we have created a separate playlist for this, and you will find this in the link of the playlist in the description box. So you will find all these one shot videos in those in that playlist. Okay, so let us continue. So so today we'll be going to learn aldehyde, ketones, and carboxylic acids. Okay, aldehydes, ketones, and carboxylic acids. So first we'll be going off with the name reaction. Okay, this section, name reaction section, is very important for CBSC or ISC. The questions generally come from here. Many questions come generally from here, and in JE also, this section is very important because sometimes they directly give you from this name reactions only. So let us come to the first point. Okay, so see, this is highlighted. So Hell-Bollard-Zelensky reaction or HVZ reaction. Okay, so you also call it as HVZ reaction. Let me put a mark here. Okay, so also known as HVZ or Hell-Bollard-Zelensky reaction. So RCH2COH when reacted with red phosphorus and a halide ion and a halide molecule, halide gas, F2Cl2, okay, I2, and water, it gives RCHX and COOH. Okay, so see, this is an alkyl group. Okay, this R is an alkyl group, and this is a CH2, and the CH2 attached to this COOH group, this carbon is known as the alpha carbon. Okay, so any carbon attached directly to COOH group is an alpha carbon. Okay, and this hydrogen is known, this two hydrogen molecules, this there are two hydrogen molecules, so this hydrogen is known as alpha hydrogen. Okay, so in this reaction what happens is that one alpha hydrogen is replaced by an halide. Okay, so it's replaced by a halogen actually. So one alpha hydrogen, this is an alpha hydrogen. Okay, this is an alpha hydrogen. One alpha hydrogen is replaced by one halogen molecule. Okay, so like remember the term red phosphorus. Okay, red phosphorus is important. Red phosphorus, so RCH to COOH, that C is that carbon is attached to COOH group, is known as alpha carbon, and that hydrogen is that those two hydrogens are known as alpha hydrogen. One alpha hydrogen is replaced by an halogen. Okay, one alpha hydrogen is replaced by an halogen, and red phosphorus is used. So if when we use red phosphorus and halogen molecule in the presence of water, we get R, the one alpha hydrogen is replaced by a halogen. Okay, so one alpha hydrogen is replaced by a halogen, and the entire thing remains same. Okay, so I hope this is clear. So I hope this thing is very clear to you guys, that one alpha hydrogen is replaced by one halogen. Just remember the reagent, it's red phosphorus. So in case of Hell-Bollard-Zelensky, you use red phosphorus and halogen. Okay, let us come to the next reaction. Okay, there is a Rosenman reduction. Okay, Rosenman reduction. So RC double bond O Cl gives, in the presence of hydrogen, palladium and BaSO4, palladium and BaSO4. This is also known as quinoline. This thing is a palladium and BaSO4 is also known as quinoline. So gives RC double bond O H plus HCl. Okay, so just see the thing. This chlorine. Okay, this chlorine is replaced by hydrogen. Okay, so there are two hydrogen here, H2. Okay, so in this two hydrogen, one hydrogen reacts like this bond breaks, this carbon chlorine bond breaks, and one H bond H breaks here, H bond H breaks here. So one hydrogen bond breaks, and one hydrogen of this hydrogen molecule reacts with chlorine it to form HCl, and due to the presence of a positive charge here, one hydrogen atom also reacts with this carbon and forms an aldehyde. So this is the thing. So RC double bond of Cl gives in presence of H2 and PDBSO4 or quinoline. Quinoline, this they might give you this term anyhow. So remember this term PDBSF for a quinoline. So this is a thing. So RC double bond OH, this gives a aldehyde. Okay, this group is known as a aldehyde group. So this is the thing. I'll highlight the thing. So H2, one hydrogen of this thing reacts with fluorine to form HCl, and one hydrogen reacts with this carbon and forms C double bond OH. Okay, so this is a aldehyde. Okay, with the alkyl group, R is an alkyl group. Okay, R is always an alkyl group. Let me write it. Okay, R is an alkyl group. Okay, so R is an alkyl group here. Okay, so Rosenman reduction we use hydrogen and PDBSO4, PD and BSO4 or quinoline. Okay, we use quinoline also. So gives RC double bond to Cl, RC double bond O Cl on presence of this like the reaction intermediates or the catalyst gives an aldehyde RC double bond OH plus HCl. Okay, just see this thing. One hydrogen reacts with this chlorine HCl and one hydrogen reacts with this carbon forming aldehyde. I hope this is clear. Okay, Rosenman reduction is done. Now comes the Stephens reduction. Okay, so like Stephens reduction is cyanide. Okay, RCN reacts with SnCl2 and HCl in the presence of H2O gives RCH. Okay, so here a cyanide RCN in presence of SnCl2. This reaction is important. So a cyanide RCN when reacts with SnCl2 and HCl in presence of water gives an aldehyde. Okay, so the reaction mechanism is a bit complicated, so I will not be discussing in this in a one shot video because reaction in like the reaction mechanism don't come in the board exams, not in JE also sometimes. So yeah, so in Stephens reduction a cyanide is converted to an aldehyde. Okay, a cyanide is converted to an aldehyde. Okay, CN group is replaced with a CHO group. Here a chlorine group is replaced with H. Here a cyanide group CN group is replaced with CHO. Okay, so earlier, so they see many people like they have a common misconception of interchanging these two, and they like generally forget which one is what. So RC double bond to Cl, when Rosenman is RC double bond to Cl, in presence of H2 and PTBSO or quinoline gives RC double bond to H plus HCl. Okay, and in Stephens reduction, R cyanide group RCN plus SnCl2 plus HCl plus H2O gives RCHO. Okay, it's a aldehyde group, gives an aldehyde. Cyanide to aldehyde in Stephens, and chlorine to hydrogen in Rosenmund. Okay, important thing. Okay, remember this. Remember the two reactions by heart. We'll be providing the document link to you also, guys. So please see from there. So now comes the Itard's reaction. Okay, now comes the Itard's reaction. Okay, so this CH2 group, this is a chromyl chloride. Okay, this thing is known as chromyl chloride. So I just write this here. Chromyl chloride. Done. So this is a carbon disulfide. It is acts as a solvent. I'll write it here also. Sorry. Inert solvent. Okay. So yeah, this is an anisole. Okay. This thing is an anisole. Anisole in presence of chromyl chloride CrO2Cl2. Remember the things. You need to remember these things by heart. Okay. So remember these things. So anisole in presence of chromyl chloride CrO2Cl2. Okay. CrO2Cl2 in presence of an inert solvent. Like note this time in Itard's reaction, if we use an inert solvent, this carbon disulfide. Carbon disulfide is an inert solvent. So in presence of an inert solvent, in presence of carbon disulfide, we have this reaction. So there are three hydrogens, right? So one hydrogen remains intact, and the other two hydrogens are like reacted with this compound. Okay, the other two hydrogens reacts with this compound CrO2Cl2 and forms this compound. This is a reaction intermediate. This is not a final product, and when it on hydrolysis with H2O on water, it gives a aldehyde. So benzaldehyde gives a benzaldehyde. Okay, so CH3 group in Itard's reaction, CH3 group is replaced by a aldehyde. Okay, it's replaced by a CHO group. So in Rosenman, chlorine group is replaced by H. Stephens reaction, cyanide group is converted to CHO group. In Itard's reaction, CH3 group is converted to CHO group. Okay, so see, like you guys will ask that how can we like recognize a reaction, which one is what reaction. Okay, this will like you have to see the like the uh, reactants, right? So you need to see the catalyst used, you need to see the solvent used, and you need to see the many things used, and then you need to conclude that which reaction is that. Okay, so see, some if someone doesn't mention this term, Richard's reaction, okay, I'll get to understand by seeing this reagent, and by seeing this solvent, I'll get to know that's the Itard's reaction. Okay, so like memorize the solvent. Solvent is an inert solvent, carbon disulfide, and the reagent uses bromyl fluoride or CrO2 Cl2. What is the action? This anisole, which has CH3 group attached to a benzene ring, is converted to CHO group, and it forms benzaldehyde. This is benzaldehyde. Okay, if you want to remember this reaction intermediate, you can remember, or else this is the final product. Okay, this is benzaldehyde. Okay, I just note it here. This is benzaldehyde. Okay, this is benzaldehyde. It's carbon disulfide. Okay, carbon is inert solvent, and it forms benzaldehyde. The CH3 group of this thing is converted to CHO group. Okay, this is known as Itard's reaction. Okay, now let us move on. Okay. Now comes the Gatterman-Koch reaction. Okay. This thing is important, very important. Gatterman-Koch reaction. Okay. So benzene, when carbon monoxide plus HCl in presence of anhydrous AlCl3 gives benzaldehyde. Okay. This thing is very important here. Benzene in the presence of carbon monoxide, HCl, and anhydrous LCl3 is benzaldehyde. Okay, so a CHO group here. See here, there was no CHO group. Okay, there's nothing, and now CHO group is added. So carbon monoxide with HCl and anhydrous LCl3 adds a CHO group. Okay, benzene to benzaldehyde. Okay, benzene to benzaldehyde. Okay. So here, see, I have converted. This is an application of this reaction also. See, when you are learning some name reactions in organic chemistry, the question setters in boards or in JE, they don't give directly these terms. Okay, they don't give those. Okay, they want to test your application capability. So they want to test that how much you can apply the things that you have learned. So you need to apply the things simultaneously in your organic conversions also. So if someone tells you to convert aniline to benzaldehyde, okay, so you need to first convert aniline to benzene and then benzene to benzaldehyde to Gatterman-Koch reaction. See, it's a beautiful application. So aniline, you don't know what is aniline right now, but we will study in the chapter nitrogen containing compounds. So aniline, so aniline is converted to benzene, and then benzene is converted to benzaldehyde. Okay, so benzene to benzaldehyde we know, benzene to benzaldehyde we can convert through Gatterman-Koch reaction. Okay, we can convert the Gatterman-Koch reaction to benzene to benzaldehyde. So it's a easy application, right? So I've written application of this also, aniline to benzaldehyde. Okay, this is the thing. So benzene, carbon monoxide, HCl, anhydrous AlCl3 gives CHO benzaldehyde. The CHO group is added. Okay, Gatterman-Koch reaction. Okay, I would say just take a printout of these notes if you want to like do not like write these things up. Just take a printout of these notes and study from here. Go through it once or twice again after this video ends. I will explain the things in the video, but if you are not satisfied, then you can again you should go again through the video, because you need at the end of the day you need to remember the stuff. So it's your call. So take a printout or take the notes, whatever is there in the PDF. So it will help you in the future in the long run. Okay, done. So use of dilute HgSO4 and dilute H2SO4. So CH triple bond CH plus H2O gives with the presence of dilute H2SO4 and HgSO4 gives CH2 double bond CHOH. Okay, so see H2O is, so H2O is H and OH. Okay, so H bond OH. Okay, so if so H bond OH. Okay, so H2O is water is H bond OH. Okay, so here one OH group is substituted with CH. Okay, so one bond, this one breaks, one OH group is substituted one on first carbon. Okay, on first carbon one OH is substituted. Okay, okay, and one hydrogen is substituted on this carbon, okay, one hydrogen is substituted on this carbon, okay. See, so when one carbon is substituted on this carbon, it gives CH2 double bond, and when one carbon is substituted, one OH group is substituted on this, so CHOH, okay. This is the thing, and this is known as tautomerism. This compound is less stable, so it automatically interchanges into this form, okay. Is automatically interchanges into this form, is known as tautomer, okay. Tautomerism. Tautomerism. This is known as tautomerism. It automatically converts into CH3CHO. Okay, so CH2CHOH. Okay, so one hydrogen comes from this. Okay, so sorry. So this oxygen is to hydrogen bond breaks. Oxygen acquires a negative charge. Okay, this thing is done, and this all bond also breaks. Okay, this bond breaks, this bond breaks here, so there is a negative charge on this carbon, and hydrogen, this hydrogen oxygen bond, OH bond breaks, O is to H bond breaks, this hydrogen acquires positive charge, okay, so it joins this CH3, okay, this carbon, so it becomes CH2, it becomes CH3, it becomes CH3, and since there is a partial delta negative charge on the oxygen and there is a delta positive charge on carbon, so they also form a bond, single bond. So earlier there was a bond, and again one bond is formed. This one double bond. So CH3 C double bond O H. It gives a CHO group. Okay, C double bond O H gives CHO group, gives CH3 CHO. Okay, you might know this from class 11 so organic chemistry. What is tautomerism? So this is CH3CHO, this is tautomerism. So just note the reagent dilute H2SO4 and HgSO4. This is very important. Okay, like many students tends to miss out this portion. So this is the use of dilute HgSO4 and dilute H2SO4. This is very important here. So CH the triple bond CH, okay, ethane plus H2O, dilute H2SO4, dilute HgSO4. One OH group is substituted on this, and one H is substituted on this. And by tautomerism, it converts into the most stable form, that is an aldehyde. Okay, CH3CHO. So now let us see this compound. Okay, CH3C double triple bond CH plus H2SO4 with dilute HgSO4 and dilute H2SO4. Okay, now OH is added to this central carbon and H is added to this carbon, okay. So you might be thinking that why is this happening, why didn't OH group like attach here, why did only attach on this carbon, not on this carbon, okay. So this is the Markovnikov rule, okay, this is the Markovnikov rule, you might know, due to Markovnikov rule. I'll just write it here. Due to Markovnikov rule, okay. So why this OH came only here only, okay, why it came here only, right, it might have come here also, right, CH3C double bond C OH, and here only an hydrogen atom would have been replaced, okay, why it didn't happen? So the rule is that the OH group, okay, the OH group always substitutes the least is always attached to the least substituted carbon, okay. So this carbon here is the least substituted carbon, it has no reactions with hydrogen, so it is the least substituted carbon. So here OH group is attached, okay, so here OH group is attached, so CH3 C triple bond CH, so here carbon the OH is the least substituted carbon, okay, note the term least substituted carbon. So since it is the least substituted carbon, OH comes and attaches here, okay, this is the rule to Markovnikov rule. So OH attaches to the least substituted carbon. I'm repeating myself, OH substituted to the least substituted carbon. This is central carbon, okay, this carbon, okay. So this carbon OH group and H, that hydrogen that is left from the water, this hydrogen attaches to the this CH group, okay, this CH group. This CH group becomes CH2. So CH3 COH CH2. Okay, sorry, this thing will not be there. Sorry, this hydrogen will not be there. This is a mistake. Sorry, this is a mistake here. This hydrogen will not be there. It's only CH3 COH and double bond CH2. This hydrogen will not be there. Okay, sorry. So It again converts by tautomerism and becomes CH3 C double bond O CH3, okay, by tautomerism. This is also by tautomerism, okay. So this interchanging is also tautomerism, because this hydrogen bond, this oxygen hydrogen bond breaks. It again goes here, and carbon develops partial negative, partial positive, and this develops partial negative. So again C double bond one one double bond is formed. So CH3 C double bond CH3. Okay. This again the same reason by tautomerism. Okay, by tautomerism. Okay, by same tautomerism. I hope the concept is clear now. The OH group always substitutes the least substituted carbon. Okay, so here, so you will ask that why it didn't happen in this case. Why didn't I mention? Because both the carbon are of the same order. Okay, both the carbons are equally substituted, so it can enter any carbon. Not if it can enter this carbon also. This OH group can enter this carbon also. Okay, this carbon also. Okay, it is not necessary that it will enter this carbon only. Okay, this is the thing. But in this case, this carbon is the least substituted, so the like OH group will attach to this thing. Okay, OH group will attach to this thing, this carbon. Okay, I hope this is clear. OH group is attached to the least substituted carbon. Okay. Okay, now let's come to the next kind of reaction. This was the use of dilute H2SO4 and HGSO4. Okay, mercury sulfate oxide, mercury sulfate. So dilute HGSO4 and dilute H2SO4. Okay. Now comes Clemenson's reduction. Okay, now earlier we learned yes, defense reduction. Earlier we learned uh, Rosenman reduction. Now we'll learn Clemenson reduction. Okay, so and this thing was the use of dilute H2SO4 and dilute HgSO4. Okay, Clemenson reduction is that C double bond O. This like this ketonic group C double bond O group on reaction with Z and Hg, it's a zinc amalgam. It's a Z and Hg is a zinc amalgam. I hope you know what's an amalgam. So on reaction concentrated HCl gives CH2 group. Okay, so the main thing in Clemenson's reduction is that any ketonic group, okay, C double bond group, this any C double bond group on reaction with Z and Hg, zinc amalgam, and concentrated HCl, not the term, concentrated HCl gives this ketonic C double bond group is converted to CH2 group. Okay, any C double bond group is converted to CH2 group. This is important here. So any C double bond group on reaction with zinc amalgam is with the concentrated HCl is converted to CH2 group. C double bond group is converted to CH2 group. Okay, this is known as Clemenson reduction. Okay, let us move on. Right, Wolff-Kishner reduction. Okay, so this Wolff-Kishner reduction is C double bond the same thing, the ketonic group on reaction with hydrazine NH2 NH2. This is known as hydrazine. Okay, this is known as hydrazine. I'll note this thing here. On reaction with hydrazine forms C like this C double bond O is replaced with NH2. Okay, and C here H2 reacts with this O, forms H2O, and the leftover part is NH2. This NH2 is left. So C double bond O and NH2. So this thing on treatment with ethylene glycol and KOH. Okay, this thing on treatment with ethylene glycol and KOH gives CH2 and plus N2 is released. Nitrogen gas is released here. Okay, you might get a question that which gas is released on Wolff-Kishner reduction. So nitrogen gas is released on Wolff-Kishner reduction. Okay, so C double bond O group is again like changed to CH2 group. Okay, C double bond O group is changed to CH2 group. In this case also, okay, and NH2 group is like NH2 NH2, this hydrazine is converted to this thing, and this compound on treatment with ethylene glycol and KOH gives CH2 plus NH2. Okay, CH2 group, C double bond group is converted to CH2 and N2 nitrogen gas is released. Okay, so we will continue in the next part. Okay, thank you. So hello guys, let us continue from where we had left. So we had done till Wolff-Kishner reduction earlier. So I hope you are clear with the Wolff-Kishner reduction. So I'll just explain it like in a very fast way. So C double bond group on treatment with hydrazine, one H2 is removed from here, one H2 is removed from from NH2, one H2 is removed, and it reacts with this forming H2O and forming this compound. Okay, So C double bond N, the single bond NH2. Okay, and this compound on treatment with ethylene glycol and potassium hydroxide KOH gives like a CH2 plus N2. So C double bond O ketonic group is replaced with CH2 in both the cases. In Clemmensen reduction also we had seen that C double bond O group is replaced by CH2 group, and here also we see that C double bond O group is replaced with CH2 group. Okay, so both the things are same, but the reagents are different in both the reductions. Clemmensen and Wolff-Kirchner, both the reagents are different. Okay, so let us move on, right? So Popov's rule. Okay, Popov's rule. So let us see what is the Popov's rule. So when ketone undergoes cleavage while oxidation, C double bond O group goes with the smaller alkyl part. So yeah, so Popov's rule says that when ketones undergoes cleavage or oxidation, ketonic group C double bond O group goes with the smaller alkyl part. So let us see with an example. Okay, let us see this with an example. So CH3, CH2, C double bond O, CH3. Okay, so we have a compound here. Okay, CH3, CH2, C double bond O, CH3. We are performing oxidation here. This is nascent oxygen. Okay, this is nascent oxygen. We are performing oxidation here. So in this case, the bond will break from here, and this bond breaks, and it forms CH3. CH2 group is changed to C double OH group. So CH3 group CH3, this CH2 is changed to C double H group, and this thing has CH3 C double bond is already there. CH3 C double bond is already there, and one OH group is extra added here. Okay, so CH3 C double bond OH. So CH3 COOH is formed. So let us see. So you might question that, like, why didn't it break from here? So why didn't it break from here, right? Why didn't it break from here? So why did it break from here only? This is because this is an alkyl group. This CH3 is an alkyl group. Okay, and this thing is also an alkyl group. This thing is also an alkyl group. CH3 CH2 gives, and the C2H5 is also an alkyl group. Okay, so C2H5 is also an alkyl group, and CH is also an alkyl group. So which one is a smaller alkyl group, right? Methane is smaller alkyl group, methyl group is smaller, or ethyl group is smaller. So of course methyl group will be smaller. Okay, so methyl group will be smaller. So this is the thing. So methyl group will be obviously smaller. So C double bond O will go with this smaller alkyl group. If there was an even smaller alkyl group, then C double bond O would have gone with that smaller alkyl group. See, so see this acid C double bond OH group. Okay, this acid will be formed with the smaller alkyl group. So CH3, the bond will break. If the bond breaks from here, this C double bond O will go with CH3 CH2. Okay, and if the bond has broken from here, then this C double bond O group has gone with CH3. Okay, so note the difference. So if it would have been broken from here, then the thing will be formed is CH3 CH2 C double bond O OH. Okay, and it will be formed HCHO. Okay, this CH3 will be converted to HCHO. Okay, HC double H, sorry. Okay, and if it since it has broken from here, so it will be CH3 C double bond O, CH3 C double bond O, and one OH group will be added. So CH3 C double bond O, OH is added, and CH3 double OH is formed. Okay, so this is the concept. So remember the rule. So when ketone, this is a ketone, right? This is a ketone. It has C double bond O group. So when ketone undergoes cleavage while oxidation, C double bond O group goes with the smaller alkyl part. Since it's a smaller alkyl part, so it has gone with the smaller C double bond O group has gone with the smaller alkyl part. Okay. So now comes one of the most important is the iodoform reaction. Okay, so iodoform reaction is a very important reaction. It comes in both. So I have like made a balanced reaction for you guys. Just remember the balanced form only, because in board exams you are asked in a balanced form only. Okay, so just remember this. So any compound with a ketomethyl group, this is known as a ketomethyl group. C double bond or CH3, this is known as a ketomethyl group, and R can be any alkyl group. Okay, so R doesn't matter. R is an alkyl group, it can be any alkyl group, methane, ethane, anything. Okay, so it can be any alkyl group or any hydrocarbon, but if any compound contains C double bond or CH3 group, it will perform iodoform reaction. Okay, so you might get a question also here that like they will give you four compounds and ask to identify which one will undergo iodoform reaction. So any compound with a ketomethyl group, C double bond CH3 group, will undergo iodoform reaction. This is must. Okay, and this group must be present in the compound. C double bond or CH3 group must be present in the compound. Okay, then only it will undergo iodoform reaction, or else no iodoform reaction takes place. So C double bond or CH3 group undergo like this. This must be present. This is the most important and the main criteria for compound to go undergo iodoform reaction. So R is R is any alkyl group. Okay, R is any alkyl group. Doesn't depend. I'll just like name it here. Ketomethyl group. Okay. So C double bond or CH3 is a ketomethyl group, and one this it is the main criteria for something to undergo like iodoform reaction. So this ketomethyl group, or any this is or any ketone, right? Any ketone here plus C 3I2 plus 4NaOH gives CHI3. This is iodoform. Okay, this is iodoform. CHI3 is iodoform. RC double bond ONA 3NaI and 3H2. Okay, this is a balanced reaction. So any organic compound containing a ketomethyl group C double bond to CH3 group upon reaction with 3 moles of 3I2 plus 4 NaOH, 3I2 plus 4 NaOH gives iodoform is CHI3. Okay, chloroform is CHCl3, and the same iodoform is CHI3. So if CHI3, RCONA, this R is the alkyl group, say RCONA, CH3CONA, C2H5CONA, anything. R is an alkyl group plus 3NaI plus 3H2. Okay, this is the thing. So gives iodoform. So any compound containing ketomethyl group, any organic compound containing ketomethyl group plus 3I2 plus 4 NaOH gives CHI3 plus RCONA gives 3 NaI and 3H2. Okay, learn this by heart and learn in the balanced reaction. Okay, how many moles? Like 3I2 and 4 NaOH. Okay, this is important. And also remember that a ketomethyl group must be present in case of iodoform reaction. You will be asked a question from there also. So now comes to the most important part, that is aldol condensation. Okay, so this is aldol condensation. So let us see what is aldol condensation. So there are two organic compounds with a ketone group, ketonic group. C double bond group is present here, or LD. You can also consider it as the aldehyde group also in both the cases. Okay, so the carbon. So see, both the compounds are same. This is CH3 C double bond OH, and this is also CH3 C double bond OH. See, I have written the three hydrogen in the other form. These are three CH3 C double bond OH. Both are the same compounds. Since both are the same compounds, we name is a direct aldol condensation. Direct means both the reacting compounds are equal and same. So see, in both the cases, these things are same. CH3 C double bond OH and CH3 C double bond OH. So both AA combination or direct aldol condensation. Okay. So AA condensation or direct aldol condensation. Okay. So both the compounds are same. So we like term this as direct aldol condensation. So in this, so the first step in this thing is that take any one of, because both are similar. Take any one, doesn't matter. So take any one. The carbon present next to the aldehyde group or next to the ketonic group. The note my words, the carbon present next to the aldehyde group or the ketonic group is termed as alpha hydrogen. Is termed as alpha hydrogen. This is the alpha hydrogen. Okay, so this is alpha hydrogen. So this is alpha carbon. So this is alpha carbon. So any carbon present next to a aldehyde group or a ketonic group is termed as alpha carbon, and any hydrogen attached to the alpha carbon is known as alpha hydrogen. So any hydrogen attached to the alpha carbon is known as alpha hydrogen. Okay, so what happens is that, see, this hydrogen moves here. This hydrogen combines with this the, see, there's a similar another compound there which is waiting to be reacted. So this alpha hydrogen reacts with this oxygen, forming OH, forms OH, done, and this CH2, and this hydrogen also remains, and a direct bond is formed. I am giving you a shortcut because in many, I have seen in many YouTube channels they teach it by a very difficult mechanism, and that mechanism becomes difficult for students to grab at first. So it becomes difficult for them to answer the question. So I have just formed a like a general idea, a general process or general steps for you to just to like you can solve these things easily. Okay, so one of the alpha hydrogen goes and reacts to this oxygen, making this oxygen as OH. Make this oxygen as OH. Okay, done. OH is done. This hydrogen remains intact, and one bond is formed between these two carbon. The alpha carbon of the previous compound with the carbon of the other compound present. Okay, so oxygen, so the double bond, okay. So one alpha hydrogen goes and makes that oxygen as OH. It becomes a OH group. See this oxygen on reacting with this hydrogen has formed OH group. This double bond is removed and a single bond is formed. Okay, I hope you get it. And this hydrogen remains intact. So this hydrogen remains intact, and one single bond is found between these two compounds. See, after one hydrogen is gone from here, CH2 remains. So in this compound, CH2 remains, and this CH2 is present here. Okay. After one hydrogen is gone from alpha carbon, two hydrogen remains. So CH2, C double bond to CH2. This is a general method. So after you practice lot and lot from this section, you will get to know what is diet alcohol condensation. It is very easy. You might seem it difficult at first, but it's very easy. Okay, just oxygen is converted to OH group, and this a single bond is formed between the two carbons. Okay, this just as simple as that. Okay, as simple as that. So let us see the conditions. Okay, so alveolar condensation will only takes place when there is alpha hydrogen present. So presence of alpha hydrogen is a deciding factor. So presence of alpha hydrogen is a deciding factor for alveolar condensation. If there is no alpha hydrogen, see in this case alpha hydrogen is present, but in other compounds, if alpha hydrogen is not present, then it will happen that no aldehyde condensation takes place. Okay, and here as a reagent, a dilute base is used, that is 10% NaOH. So you have, I guess you have encountered that term. So 10% of any base, it's a very dilute base. So 10% of any base must be present, or a dilute base must be present in case of aldehyde condensation, or else it will not take place. So let us see the conditions. There is a alpha hydrogen must be present, and a dilute base must be present. Okay, so this is the thing. So now let us move on to the next reaction. Right? This is a Claisen-Smith reaction. Claisen-Smith reaction is very important in this case. So Claisen-Smith reaction. We have benzaldehyde. Okay, we have benzaldehyde and formaldehyde. Okay, so we have benzaldehyde and formaldehyde here. So 10% NaOH. So that the moment you see 10% NaOH, you strike that it's a aldol condensation. Okay, aldol condensation, and you also see this here that alpha carbon is present. Okay, so you see that alpha carbon is present, you see that 10% NaOH is present. That means it's a allyl condensation. You're sure now, right? So in this way, like they will not mention you that this reaction is preceded by allyl condensation. Okay, so you need to identify what kind of reaction you can apply there. Okay, so main thing is applying. So 10% NaOH is there, alpha hydrogen is there, alpha carbon is there, so alpha hydrogen is also there. So what do you strike? It's allyl condensation. So let us do the allyl condensation. So what I have told you, right? This is alpha hydrogen. So this hydrogen will go with combine with this, forming this will form a OH group. Okay, so the benzene ring is there. See, it forms a OH group. So double bond, from double bond it forms OH group. So OH is formed, and the H remains intact here. The H remains intact here. OH group is formed, and now what I said, a single bond will be formed between the two carbons. Okay, so now the single bond is formed between two carbons, and after one hydrogen is gone, two hydrogens are left. So CH2 and CH as earlier it was present. Okay, things are very easy. See, I followed my own steps. So double bond O is converted to OH. Double bond O on reacting with one alpha hydrogen is converted to OH. Done. The H remains intact. One single bond is formed between the two carbons. One single bond is formed between the two carbons, and these two carbons CH2. Okay, so carbon single bond CH2, single bond CH. This is the thing. Okay, so now comes to like see, this was Claisen-Smith reaction. Okay, this is the very famous name reaction. This is the Claisen-Smith reaction. So let us see what is this. So after we heat this, as we have learned in class 11, after heating H2O is released. Okay, after heating H2O is released. So how can we release H2O? Okay, so this OH group, it has a OH group here. So it has a OH group here, and if one hydrogen from this thing, this CH2, if one hydrogen from CH2 is removed, then H from this CH2 is removed, and OH from this COH is removed. Okay, so this OH is removed, and this H is removed. Okay, this H is removed. Okay, like I don't know how to just let me sort this out. Yeah. So one H from this is removed. Okay. Okay. So one H. Okay. So one H from this is removed, and one H from this is OH from this is removed. Okay. So if one when we remove one H from this and one OH from this, so a double bond is formed in between those. Okay. So after heating, this is known as cinnamoldehyde. This compound is known as cinnamoldehyde. Okay. This thing is very important for NEET because many times it came in NEET. So let us see. So yeah, so I hope you know what is dehydration. You know, I hope you have studied in class 11 the things of dehydration, or you can check out our lecture where we have explained dehydration in like in details. So let us check that out in our playlist of organic chemistry class 11. So here there we have explained like what is dehydration, how it proceeds, what are the steps involved in dehydration. So if you have any like confusion in dehydration, or else if you can understand, it's well and good. Okay. So one OH is removed from here and one H is removed from here. So if from CH2 one H is removed, so it forms CH. From CH2 one H is removed, it forms CH. Okay, and a double bond is formed here because this OH minus removes, this H removes, OH removes, H removes, and double bond is replaced here. Okay, so I hope you know the like as I earlier said. If you have any doubt, check out our organic chemistry class 11 playlist. There we have discussed like how dehydration occurs. So this is the thing. So this remember this compound. So cinnamaldehyde is very important. So how is, so you can also get a like a question in boards that how cinnamaldehyde is prepared. So cinnamaldehyde is prepared by the direct aldol condensation of benzaldehyde. Okay. So cinnamaldehyde is formed by the aldol condensation of benzaldehyde with methanaldehyde. Okay. Benzaldehyde with methanaldehyde. Benzaldehyde with methanaldehyde. Aldol condensation of benzaldehyde with methanaldehyde. Okay, thing is done. And name the reaction. It is Claisen-Smith reaction. Okay, this thing is very important. You might be given to write the, you might be given a question boards that write the Claisen-Smith reaction. Okay, so you need to remember the Claisen-Smith reaction. It aldol condensation of benzaldehyde and methanaldehyde occurs, and after that we heat it and form cinnamaldehyde. Okay, the aldol, after the aldol condensation, the product is formed and that product is heated to form benzaldehyde, cinnamaldehyde. Sorry. So cinnamaldehyde is formed by Claisen-Smith reaction. Cinnamaldehyde is formed by Claisen-Smith reaction. I hope this is clear. Let us move on. Okay? The names might seem confusing to you guys, but by the time you read more, by revise more, you will get to like you'll get familiar with the terms and it will be a cakewalk for you guys. Okay, so that is why I am repeating more and more times so that you guys like can remember the things from the video itself. Okay, now comes the Perkins condensation. This is very important. Many students tend to forget. Many students like they know everything, but they don't know Perkins condensation. Okay, so Perkins condensation is a benzaldehyde. Okay, this is the benzaldehyde done. Benzaldehyde is done. This is benzaldehyde. This is acetic anhydride. Okay, this is acetic anhydride. Remember the formula. This is acetic anhydride. It gives a salt of that, so acidic, this see acetic anhydride is formed from acetic acid. Okay, so in this the Perkins condensation says that the acetic anhydride, that is the acid from which the acetic anhydride is like retrieved or made. So from that acid should have a salt of sodium salt of that acid should be present as a catalyst. Okay, this is the thing. So this is the acidic anhydride. Acidic anhydride is obtained from acetic acid. So acetic acid. So as according to the rules of the reaction, it says that sodium salt of the primary acid should be used. So what was the primary acid? It is acetic acid. So sodium salt of acetic acid, it gives CH3COONA. Okay. So benzaldehyde on reaction with acetic anhydride and sodium salt of acetic acid on heating forms cinnamic acid. This thing is very important. Like note this thing, and acetic acid is formed. Okay, so benzaldehyde on reaction with acetic anhydride on in the presence of sodium salt of acetic acid as a catalyst forms cinnamic acid and acetic acid. Okay, so yeah, so in Claisen-Smith reaction, we observed that cinnamaldehyde was formed in Claisen-Smith reaction. Here in Perkins condensation, cinnamic acid is formed. Okay, so don't just note the remember the name cinnamic acid. You must remember the compound also. This is cinnamic acid. Okay, so benzene ring with CH double one CH single one C double OH. Okay, this is cinnamic acid. Okay, remember the name. So benzaldehyde, acetic anhydride in presence of catalyst of sodium salt of acetic acid gives cinnamic acid and acetic acid. Okay, so this is the thing. So let us move on, go through this one, because you need to like everything. It doesn't it doesn't work like as a shortcut, or you can just see the video and you are mastered chemistry. So you must, like, after the video is over, we have explained you everything, just go through the notes once. Okay, will be providing the drive link in the description box. So no, go through the notes after the class is over, and you will, if you have any doubt, please contact us, because after going through the notes, I guess you will not have any doubt. But if you still have some doubt, we can like clear it out on a personal basis. Okay, so now benzoin condensation. Okay, this is benzoin condensation. Benzoin condensation, we have two moles of benzaldehyde. Okay, 2 moles of benzaldehyde, like I write it here. 2 moles of benzaldehyde. 2 moles of benzaldehyde is taken. So 2 moles of benzaldehyde is taken, and it in the presence of C2H5OH and alcoholic KCN. Okay, so C2H5OH and alcoholic KCN. Note the reagents. Okay, note the reagents, because it's very important. Like many students like forget, they use 10% in average. Okay, so in benzoin condensation, 2 moles of benzaldehyde is reacted with 2 moles of benzaldehyde is reacted in presence of C2H5OH and alcoholic KCN. And it undergoes aldol condensation. Okay, it undergoes aldol condensation, right? So this is the thing, it undergoes aldol condensation. So let us see. It undergoes aldol condensation. So as we know that, like, one hydrogen from alpha, this thing is converted to this OH, or double bond O group is converted to OH group, and one single bond is formed between these two. Okay, that is the entire point. So one hydrogen from this alpha carbon, one hydrogen from this alpha carbon is restored to this double bond group. It forms OH group. So C, one H and one OH, and C double bond group remains as it is. Okay, and one single bond is formed between the two carbons. So one single bond is formed between the two carbons. So note the reagents. Many students, like, since they see this yellow condensation, they write 10% in average. Okay, it is not the case. So the reagents are C2H5OH and alcoholic KCN. In case of benzoin condensation, 2 moles of benzaldehyde undergo aldol condensation in presence of C2H5OH and alcoholic KCN. Okay, I hope this is clear. Let us move on. Right, now comes Cannizzaro reaction. Okay, this is very important here. So note, like in aldol condensation, we use 10% NaOH. Okay, so in Cannizzaro reaction, we will be using 50% NaOH. We will be using 50% NaOH. Okay, and in Cannizzaro reaction, there are no, like in allyl condensation, we had a direct combination and cross allyl condensation. Okay, in allyl condensation, we had direct allyl condensation and cross allyl condensation. So it might, the two compounds might be same, or two compounds might be different. Okay, but in this Cannizzaro reaction, in any of the Cannizzaro reactions, the two compounds, the two reacting compounds must be same. Okay, must be same and equal. Okay, so here methanol formaldehyde, sorry, HCHO and HCH. Okay, in presence of 50% NaOH gives HCONA and HCH2OH. Okay, so why have I written in this form? This HCONA is oxidized, and this HCH2OH is reduced. Okay, alcohols are always a reduced product, and acids are always an oxidized product. Okay, so why have I said that? This CHO group, this CHO group is always constant. Okay, this CHO group is always constant, and this H might be replaced with anything else. Okay, so let us see an example. See, here it was H, and here it is now a benzene ring. Here it is now a benzene ring. Earlier it was H, and now it is a benzene ring. Okay, so this CHO group is constant, and the ring or the compound attached to this CHO group is varying. Okay, so this CHO group, when like this is the general formula. So any compound, see, let us like R, if it is RCHO, if it is R bond CHO, okay, if it is R bond CHO, then it will be RCONA and RCH2OH, okay. So here R is a benzene group, okay, so benzene, so RCHO gives RCONA and RCH2OH. So RCHO, so it is benzene CHO, so 50% NaOH, so note that 50%, you need to distinguish between the two, okay, canister and aldol. So R benzene ring, so benzene CONA and benzene CH2OH, okay. So yes, this is a general formula RCH2 RCHO. So RCHO gives RCONA and RCH2OH. The alcohol is a reduced product and acid C double bond Na is a oxidized product. Okay. So if it is a benzene, it is the benzene CONA and benzene CH2OH, something like that. Benzene ring is attached to CON and benzene is CH2OH. If it is HCH, then HCONA and HCH2OH. If it is CH3CHO, then CH3CONA and CH3CH2OH. Likewise, okay. This is a general formula. This R is a general formula, like I write here. Mm, R RCONA, and will be R. This is RCH2OH, okay. So RCHO gives, in presence of 50% NaOH, gives RCONA and RCH2OH. This is a generalized formula. R can be varying from benzene ring to hydrogen to methane, anything. Okay, anything. Okay. So now crossed aldol condense called crossed Cannizzaro reaction. Okay, this is a special type of crossed Cannizzaro reaction. So if one aldehyde is formaldehyde, it will be oxidized to acid and other will be reduced to alcohol. Okay, so you might get, so in some cases you might get the two compounds different. Okay, so if out of the two compounds, if any compound is formaldehyde, okay, if any compound is formaldehyde, so then in presence of considered NaOH of 50% NaOH, like the formaldehyde will be oxidized to acid, so the acid will always be formed of HCONA, and alcohol will be formed of the other compound, okay, other aldehyde. So if out of the two compounds, if anyone is formaldehyde, then formaldehyde will always be oxidized. Formaldehyde never gets reduced. Formaldehyde never gets reduced. Formaldehyde is always oxidized to acid, okay, HCONA, and the other aldehyde will be reduced, okay. So note, formaldehyde cannot be reduced. Formaldehyde is always oxidized. It's always oxidized, okay. Formaldehyde is always oxidized, okay. Now comes the second case. So if none of them is formaldehyde, okay. So out of the two compounds, none of them is formaldehyde. Then what will happen? So each compound will undergo reduction and oxidation, and both the compounds will undergo reduction and oxidation, and total four products will be formed. Okay. So let us see these two compounds. So out of these two, none of them are none of them are formaldehyde. Okay. None of them are formaldehyde. Okay. So what will happen? This compound will undergo oxidation. This is oxidation, and this is a reduced product RCH2OH and RCONA, say CH3 whole 3. So RCONA and RCH2OH, and this compound will separately undergo oxidation and reduction. Okay, so out of the, so each compounds, if none of them is formaldehyde, then each of the compounds will undergo oxidation and reduction simultaneously. Okay, so total, so there, if there are two components, okay, so none of them are formaldehyde, then each component undergoes oxidation and reduction simultaneously. This is very important because many times it came in need, so that's why I am telling you. So understand this thing. So there are totally four compounds. So this forms two compounds, this forms two compounds, and this forms two compounds. Okay. So this forms the oxidized product, this forms a reduced product, this forms a oxidized product, this forms a reduced product. Okay, like that. Okay. So this is the thing. And in if one of the aldehyde is formaldehyde, then you know that like it will be always be oxidized, and formaldehyde is never reduced. Formaldehyde is always oxidized and never reduced. Okay, and the other aldehyde present will be reduced. Okay, other aldehyde will be reduced and the formaldehyde will be oxidized. Okay, and because of concentrated NaOH. Concentrated NaOH is important because in Cannizzaro reaction, without concentrated NaOH or concentrated base, reaction cannot proceed. Okay, so let us see. Okay, so let us continue. So since we have already learned about aldehydes, ketones, and carboxylic acid and their name reactions and the main primary questions that come from this section, so let us see the tests for these acids, like tests for this compound. So like if you are given a common salt, how do you identify? Like you will like taste it and you will see the taste and then you can like comment that it is a common salt or sodium chloride. So in the same way, all the organic compounds have some physical characteristic tests. Okay, so let us come to the first point. Okay, so this is a test for acetic acid. Okay, test for acetic acid. So acetic acid gives blood red coloration on treatment with a neutral ferric chloride solution. Okay, due to the formation of ferric acetate. So acetic acid, sorry, like I forgot to mention the, okay. So acetic acid gives blood red coloration, not only red, like it's a blood red. Okay, so and it's a coloration and not a precipitate. So I have seen many students who like confuse between red and blood red, and they, even if they remember the term blood red, they write blood red precipitate. So it's not correct. Acetic acid gives blood red coloration. Coloration is like dissolved colored solution, and precipitate, it precipitates at the bottom of the test tube. Yes, it is not a precipitate, it is a coloration and not a precipitate. Okay, so remember this term. So acetic acid gives blood red coloration on treatment with neutral. This neutral term is important. Not only ferric chloride, only neutral ferric chloride solution. On treatment with neutral ferric chloride solution due to formation of ferric acetate. Okay, so acetic acid gives blood red coloration on treatment with neutral ferric chloride solution due to formation of ferric acetate. So the term neutral and blood red coloration is important. These are the keywords that the examiners look in your answer script in boards. So neutral is very important, neutral ferric chloride and due to the formation of ferric acetate. I hope you are clear with this thing, test for acetic acid. Okay, so let us move on. So Benedict's reagent, okay. So Benedict's reagent is alkaline solution of cupric citrate. Okay. So Benedict's reagent is alkaline solution of cupric citrate. So we name the alkaline solution of cupric citrate as Benedict's reagent. Okay. I hope this is clear with you guys. So it is blue in color. So Benedict's reagent is blue in color. It fails to oxidize aromatic aldehydes. Okay, it fails to oxidize aromatic aldehydes. So I hope this is clear. So Benedict's reagent is alkaline solution of cupric citrate. It is blue in color. It fails to oxidize at aromatic aldehydes. Okay, aromatic aldehydes, but it can oxidize aliphatic aldehydes. Okay, but reddish brown precipitate of Cu2O is found on the positive test. Okay, so how will you see the reagent is blue in color? So how will you identify that given, how with the help of this reagent, how will you identify that a given compound is a aldehyde or not? So if it is a aldehyde, then reddish brown precipitate of copper 2 oxide Cu2O will be formed on positive test. Okay, so it was blue in color and reddish brown precipitate will be formed of Cu2O. In that way, you will understand that the given compound is an aldehyde. Okay, so why Cu2O? Cu2O because it contains cupric citrate. So cupric citrate contains copper. So that's why copper has a reddish brown color. So reddish brown precipitate of copper Cu2O is formed on positive test. Okay. So Benedict's reagent, it is blue in color, alkaline solution of cupric citrate. Okay. It fails to oxidize aromatic aldehydes. Done. Reddish brown precipitate of Cu2 is formed in Cu2O is formed in on positive test. Okay, this is very important. Okay, now comes Tollens. This is very important. This is a very common reagent used in chemistry. So now it is Tollens reagent. Okay, so what is Tollens reagent? Tollens reagent is ammoniacal silver nitrate solution. This is very important. This name is very important. So what is Tollens reagent? Tollens reagent is ammoniacal silver nitrate solution. I hope this is clear for you. Tollens reagent is ammoniacal silver nitrate solution. Tollens reagent is ammoniacal silver nitrate solution. Benedict's reagent was alkaline solution of cupric citrate, and Tollens reagent is ammoniacal silver nitrate solution. So what does this? So what does this reagent do? Okay, so it produces silver mirror on the sides of the test tube. Okay, so on positive test, it forms silver mirror on the sides of test tube. So by silver mirror, we want to mean that it deposits silver on the sides of the test tube. It works for both aliphatic and aromatic aldehydes. Okay, it works for both aliphatic and aromatic aldehydes. So earlier Benedict's reagent failed to oxidize aromatic aldehydes. So it means that it couldn't work for aromatic aldehydes, but it only works for aliphatic aldehyde. But in tolerance reagent, both works for both aliphatic and aromatic. It doesn't judges. It works for both aliphatic and aromatic aldehyde both. And it is tolerance reagent is ammoniacal silver nitrate solution. Since silver nitrate is present, silver is present, so it deposits silver on the sides of the test tubes, which shines like a mirror. Okay. Since it's a one-shot video, I'm not going into details, each and every details of the each and every reagent. I'm just going through the main and the most asked points. But if you want to see the entire process, and if you want to go through the entire process and know about the process, just check out our full-length video in the playlist of Organic Chemistry Class 12. Okay, this is a one-shot video. So tolerance reagent. Okay, so tolerance reagent is ammoniacal silver nitrate solution. It produces silver. Since it contains silver, the silver deposits on the sides of the test tube, forming a mirror-like structure, silver mirror. So it produces silver mirror on the sides of the test tube. Works for both aliphatic and aromatic aldehyde. Earlier Benedicts used to work only for aliphatic aldehyde, not aromatic aldehyde. Okay, it worked for only aliphatic, and it works for both aliphatic and aromatic. Tolerance works for both aliphatic and aromatic. Okay, just embed this in your mind. So now comes Fehling solution. Okay, now comes Fehling solution. So what is Fehling solution? Fehling solution is equimolar mixture of Fehling solution A. So what is Fehling solution A? Aqueous copper sulfate, aqueous CuSO4, and Fehling solution B. What is Fehling solution B? Aqueous solution of sodium potassium tartarate. So it is also known as Rochelle salt. Okay, I just put a note here. It is also known as Rochelle salt. So this is also known as Rochelle salt. Okay, so Rochelle salt. Fehling solution. So Fehling solution is composed of two components: equimolar mixture of Fehling solution A and Fehling solution B. So when you answer this question, then a question arises that what is Fehling solution A and what is Fehling solution B? So Fehling solution A is aqueous copper sulfate, aqueous CuSO4, and what is Fehling solution B? It is alkaline solution of sodium potassium tartarate, alkaline solution of sodium potassium tartrate, or Rochelle salt. So Fehling solution is composed of two elements, Fehling solution A and Fehling solution B. Equimolar mixture of Fehling solution A and Fehling solution B. Fehling solution A is aqueous copper sulfate, aqueous CuSO4, and Fehling solution B is alkaline solution of sodium potassium tartarate, alkaline solution of sodium potassium tartarate. So it works only for aliphatic aldehyde. It works for only for aliphatic aldehyde. So you need to remember this point. It works only for aliphatic aldehyde. Okay. So tolerance used to work for both aliphatic and aromatic. Fellings works only for aliphatic, and Benedict's also works only for aliphatic. Okay. So only tolerance reagent works for both, and Fellings and Benedict's reacts only works for aliphatic aldehyde. Okay, it is used in the identification of aliphatic aldehyde. So all these three reagents are used in the identification test of those particular compound. So they will give you a compound, identify this compound, whether this compound is aldehyde, alcohol, or acetic acid or something else. So to perform all the characteristic tests for that compound, yeah, I hope that you will learn this in like in your practical classes of chemistry in your school. So you will get to know this from there. So you will be given four compounds and you need to identify the things which is what. Okay, so you need to perform these solutions. So if for to confirm the presence of aldehyde, you need to perform Fehling solution test, tolerance reagent test, and Benedict's reagent test. So after you perform all these, you will get to know whether it is aliphatic or aromatic aldehyde or not. Okay, so this note the difference between the three reagents. So Benedict solution is blue in color. It forms a reddish brown precipitate of Cu2 is formed on positive test. Tolerance is ammoniacal silver solution, silver mirror test. This is also tolerance reagent test is also known as silver mirror test. Okay, tolerance reagent test is also known as silver mirror test. So also known as silver mirror test. Okay, so tolerance reagent test is also known as silver mirror test because it forms silver mirror on the side of test tube. Tolerance works for both aliphatic and aromatic aldehydes. Okay, so now comes Fehling solution. Fehling solution is equivalent to Fehling solution A and B. So what is A? You know that aqueous CuSO4. What is B? Alkaline solution of sodium potassium tartrate or Rochelle salt. It only works for aliphatic aldehyde. So just go through these three reagents properly. Just go through these three reagents properly. These are very confusing, and you need to go like multiple times to see this. But I have like repeated the things twice or thrice so that it becomes easier for you to remember. So note the difference between the three reagents. This is very important. Okay, and test for acetic acid you also know. blood red coloration on treatment with neutral ferric chloride solution due to formation of ferric acetate. So acetic acid, ferric chloride become ferric acetate. Okay, ferric chloride, acetic acid, ferric acetate. Okay, I hope this is clear. And ferric acetate is blood red in color. Okay, so let us move on. So particularly for the board students, okay, so particularly for the board students, there are some important conversions to remember. Okay, these conversions come in board exams. Okay, these conversions come in board exams, and these doesn't come in like in JE, that don't come in any competitive exam. So the students who are watching this video only for JE purpose may leave here, and the students who are interested in boards exam and in school level exams, they can, like, they should continue the video. Okay, so first conversion. Okay, so if you are asked to convert acetaldehyde to protonaldehyde, okay, so now you'll be thinking that what is protonaldehyde is a very tough thing, so भाई हमसे नहीं हो पाएगा, तो सभी होगा तुमसे, so हम है ना, सब होगा. So acetaldehyde to protonaldehyde. So what is protonaldehyde? Protonal, this compound is known as protonaldehyde. Okay, this is acetaldehyde. Okay, this is acetaldehyde. I hope you know this. This is acetaldehyde. Acetaldehyde is acetal, when it's aldehyde, acetaldehyde, and this is protonaldehyde. Okay, so how do you form? So it is formed by the aldol condensation. See, like I earlier mentioned here, that like all the conversions are just nothing but the applications of the name reactions and the mechanisms that we have learned in the theory videos. Okay, so conversions are nothing so tough. Like I have seen many people who are not able to convert one compound to another compound because they don't know how to apply. They have just like marked up the things and they don't know how to apply the things. So conversion is nothing but the application of the things that you have learned in your from your books. Okay, so we had learned aldol condensation, so dilute NaOH. So we had dilute NaOH. So if in aldol condensation, this aldol condensation, okay, so if you have 2 moles, okay, so if you have 2 moles, so 2 CH3 CH, okay, 2 CH3 CHO, aldol condensation, as we have learned earlier. Okay, so I hope you know, like you know it thoroughly, and you can do it like just by seeing without any pen and paper. So CH3 C double bond OH, that alpha hydrogen reacts with that oxygen or double bond oxygen, so it becomes OH, and a single bond is formed between the two carbons, two central carbons, I guess. I hope you understand. Two central carbons. So it forms CH3, C double bond O, COH, H, and CH2, CHO. Okay. So now it undergoes dehydration. Okay. On dehydration, one hydrogen from this compound, one hydrogen from this CH2, and OH from this is removed. So CH3, CH, double bond, CH, CHO. So one hydrogen is removed from here, and one of the OH group is removed from here. So water is removed. So one H is removed from here, one OH is removed from here, and dehydration occurs. So CH3, CH, double bond CH, single bond CHO. This is known as protonaldehyde. Okay. So I guess that you guys will be thinking that like do we need to remember the compound? Yes, you need to remember the compound, because at the end of the day you need to like write in the compound form only, in the chemical structure only. So you need to remember what is protonaldehyde, because if you forget what is protonaldehyde, then you will not be able to convert. Okay, so just remember things. These are the some basic stereotypes reaction. So like if in the exam that you are given it acetaldehyde to protonaldehyde, convert this. Okay, so like you guys are thinking that we have acetal, what, how to do these things. Okay, so these things, until and unless you see it somewhere, until and unless you have practiced somewhere, you cannot proceed. Okay, so that's why I'm practicing only the selected ones, because there are infinite number of conversions in organic chemistry, but like these are the most prominent ones that I have found in my like in the school exams and through my experience of competitive exams. So these are the things that you need to know in order to proceed with organic chemistry conversions. Okay, so acetaldehyde, it undergoes dilute NaOH, allyl condensation under dilute NaOH. So after allyl condensation, this product is formed. So after dehydration, we have already discussed the mechanism of dehydration in the theory video, in the like long video, not in the one shots. So let's just go from there. Just see from there. Okay, so H is removed from here and OH is removed from here, and double bond replaces here. Okay, so say there's a single bond. There's a single bond, and now it is a double bond here. Okay, it had a single bond, it now has a double bond. Okay, so H and OH from here is removed. This compound is known as protonaldehyde. Let us move on. So acetone to mesitryl oxide. Okay, so you guys might be thinking that what is mesitryl oxide. Okay, I guess you know what is acetone. This is acetone. This is acetone, okay. CH3 C double bond CH3 is acetone. This compound is known as mesitile oxide, okay. This compound is known as mesitile oxide, okay. Okay, so if in so it's protonaldehyde. So protonaldehyde is formed with the alveolar condensation of acetaldehyde. Okay, protonaldehyde is formed from acetaldehyde. Protonaldehyde is formed from acetaldehyde, alveolar condensation. Okay, so mesitile oxide is formed by the alveolar condensation of acetone. So earlier we learned that protonaldehyde is formed from the alveolar condensation of acetaldehyde, and mesitile oxide is formed by the alveolar condensation of acetone. Okay, so baryta, this is BaOH whole 2 is known as baryta. Let me baryta. This is barium hydroxide is also known as baryta. So acetone, in the presence of baryta, it's a weak base, so it undergoes allyl condensation. After this allyl condensation, one OH from here and one H from here. So one H from here and one OH from here. So it gets removed due to dehydration, and the double bond replaces it. There was a single bond, now it is a double bond. See, it's a single bond, now it is a double bond. So double bond replaces here after dehydration. See, the main motive of dehydration, for the students who are not getting it. So the main motive of dehydration is removal of water, H2O. So since OH is already here, so what we need to remove? H, we need to obtain H2 and we have already OH. So H is missing. So this H will replace here. This H will replace here. Okay. This H will be replacing here. I hope you know this. So this one H from this CH2 and one OH removes from here, and the double bond replaces, and the double bond replaces instead of a single bond, the double bond replaces here. Okay, and this product is known as mesitile oxide. So mesitile oxide is formed by the in the presence of baryta. Alveolar condensation takes place of acetone, and mesitile oxide is formed. So mesitile oxide from acetone in presence of baryta. Protonaldehyde is obtained by alveolar condensation of acetaldehyde. Okay, these two reactions are gone. Just remember the compound also, because you'll be lost in the exam if you don't know what is mesitile oxide. Okay, so acetaldehyde to acryldehyde. Okay, this is acryldehyde. This compound is known as acryldehyde. So this compound is known as acryldehyde. Okay, so acryldehyde is formed by the aldol condensation of formaldehyde. This is formaldehyde, and this is acetaldehyde. Okay, so it is formed by the crossed alveolar condensation, right? There's a crossed alveolar condensation we have done. So this is a alpha. This carbon is an alpha carbon. These hydrogen are alpha hydrogen, and the same like in the presence of dilute NaOH, the same mechanism of alveolar condensation persists. So one H goes to this oxygen, it forms OH, and the single bond is formed between the two central carbons. So CHH CH2 OH, single bond CH2 C double bond OH. Okay, so this is formaldehyde, this is acetaldehyde, and this is acryldehyde. Okay, so we had earlier learned protonaldehyde is formed only from acetaldehyde. Mesitile oxide is formed from mesitile oxide is formed from acetone, and acryldehyde is formed by formaldehyde and acetaldehyde. This is not like you guys might be thinking that what is the difference from the protonaldehyde? What is the difference between protonaldehyde and acryldehyde? Protonaldehyde is formed by the direct aldehyde condensation of acetaldehyde. Acryldehyde is formed by the crossed aldehyde condensation of acetaldehyde and formaldehyde. Okay, this is the main difference here. Okay, so likewise, then dehydration occurs. When dehydration occurs, this OH and one H from here removes, and the double bond replaces, and this is known as acryldehyde. This is known as acryldehyde. So acryldehyde is obtained from acetaldehyde and formaldehyde. That allyl condensation of acetaldehyde and formaldehyde. Okay. So acetaldehyde to cinnamaldehyde. Okay. So we had earlier learned this in Claisen-Smith reaction. So just like reverse the video and just go through that portion, you will be clear with that. Okay, so acetaldehyde or benzaldehyde to cinnamaldehyde. Okay, this is a very important reaction to remember. So now comes the second part. Okay, so acetaldehyde to lactic acid. Okay, so this is known as lactic acid, CH3CHOH C double H. Okay, this is known as lactic acid. So CH3CHOH C double H. Okay, this is known as lactic acid, CH3CHOH C double H. This is lactic acid. Okay, so this is acetaldehyde. Okay, this is acetaldehyde. So this is acetaldehyde. Acetaldehyde in presence of HCN cyanohydrin in presence of HCN. In presence of HCN, this double bond of oxygen, one bond breaks and forms negative charge on oxygen and positive charge on carbon. Okay, so and from this HCN, H bond CN cyanide, hydrogen is bonded with cyanide group. Okay, so H and the bond between H and CN breaks, and the positive charge develops on hydrogen, and the negative charge develops on cyanide group. So this negatively charged cyanide group, CN group, is attaches to this positively charged carbon. Okay, after the breaking of this double bond, oxygen takes negative charge and carbon takes positive charge. So negatively charged cyano group will react with this, and positively charged hydrogen will react with this oxygen. Okay, so C one over cyano group is is present here. H was already present, hydrogen was already present here. CH was already present, and when oxygen is reacted with hydrogen, forms a OH group. Okay, so just see the thing, HCN bond breaks, hydrogen is positive, cyano group is negative, and in acetaldehyde, that double bond oxygen, the one bond from the double bond breaks, oxygen takes negative charge and carbon takes positive charge. So positive will attract negative. So carbon's positive charge reacts with cyano group's negative charge, and oxygen's negative charge reacts with hydrogen's positive charge. So it becomes CH3 COH HCN. Okay, this is known as this. And after that, treatment with HCl and H2O is to this result. Okay, so CH3 is remains intact, CH3 remains intact, CH remains intact, C and H, this C and this H remains intact, CH remains intact, OH also remains intact. This cyano group, cyano group is converted to C double bond to H. Okay, so just remember the formula of lactic acid. This is very important here. This is lactic acid, CH3 CHOH C double OH. So what does this HCl and H2O does? This HCl and H2O converts cyano group, converts this cyano group to C double bond OH group. Okay, so CH acetaldehyde reacts with cyanohydrin HCl, forms a compound like by bond breaking, as I have discussed earlier. By bond breaking, it forms a compound. That compound on treatment with H2 and HCl, hydrochloric acid and water, the cyanide group is converted to C double bond H group, and all the other groups remains intact. Okay, so since you can see this CH3 group remains intact, this hydrogen group remains intact, this OH group remains intact, only cyano group, CN group, is converted to C double OH. So this is the role of HCl and H2O. Okay, this is the role of H2 and H2O and HCl. Okay, so it converts cyano group to C double bond OH group. Okay, so now comes benzaldehyde to benzelic acid. Okay, it now comes benzaldehyde to benzelic acid. So this is benzaldehyde. So this is benzaldehyde. This is cyanohydrin. So as I have said, there is oxygen bond breaks, carbon positive, oxygen negative. Here hydrogen positive and cyano group negative. So positive and negative attract. So this CN group replaces here. Oxygen reacts with a positively charged hydrogen. It forms OH group here, and then H2 and HCl. So what I have discussed earlier, this H2 and HCl will convert the cyanide group into C double bond OH group. Okay, so here cyanide group is replaced with C double bond OH group, and all the other things, and all the other things remains intact. Okay, and all the other things remain intact. Okay, so this benzene group remains intact, this OH group remains intact, this hydrogen group remains intact, only the cyano group is converted to C double bond OH group. So by the same, so this is mandelic acid. So this compound is known as mandelic acid, remember this by heart. So benzene, CH, OH, C double bond OH, this is known as mandelic acid. So and lactic acid was CH3 CHOH C double bond OH. So this is lactic acid, and when you prepare mandelic acid, CH3 group is replaced with benzene ring. Okay, so earlier it was CH3 CHOH C double bond OH, and mandelic acid is benzene ring plus CHOH C double bond OH. Okay, I guess you're clear with this thing. It's a one shot video, so I'll not go into deep. So this is the thing, benzaldehyde to mandelic acid. This is benzaldehyde on treatment with cyanohydrin HCN, bond breaking and sharing, bond breaking and like the reaction occurs. then we convert the treat it with H2 and HCl. This H2 and HCl converts cyano group into C double bond OH group. Okay. So propanoic acid to lactic acid. Okay. So this is propanoic acid. This is the formula of propanoic acid. I hope you know. It's the basics of chemistry. And, like you have already know that this is lactic acid. Okay. So this is propanoic acid and this is lactic acid. We need to reach it from here to here. Okay. So from propanoic acid, we need to reach to lactic acid. Okay. So here red phosphorus and bromine is used. Okay. So here red phosphorus and bromine is used. So I would like to come like I like the students to comment like what kind of reaction is this. Okay, so we have already learned in the like in this PDF only, like in this course only, that what kind of reaction is this. So red phosphorus and any halogen molecule. So I hope you understand that. I hope you are remembering, getting to like answer the things. So it's a Hell-Vollard-Zelensky reaction. It's an example of a Hell-Vollard-Zelensky reaction, HVZ reaction. So what we have done in HVZ reaction, red phosphorus and any halide molecule X2, any halide molecule X2 reacts with this. So here this is alpha. This carbon is an alpha hydrogen. Like if you are not familiar with these terms, then just go to the beginning of the video. I have started the video with this reaction only, Hell-Vollard-Zelensky reaction. So if you cannot like catch the things up, then just go through there and like I hope that it will be clear. And if it's not, then please contact us. Okay. So this carbon is an alpha carbon and this hydrogen is an alpha hydrogen. So we have done that in Hell-Vollard-Zelensky reaction. One alpha hydrogen is replaced by halogen atom. Okay. So red phosphorus and halogen, here halogen is bromine, Br2. So alpha hydrogen. So one alpha hydrogen is replaced with bromine. So one alpha hydrogen is replaced with bromine. Okay. So earlier it was CH2. One hydrogen is removed by bromine. So CHBr. Okay. CHBr. Okay. CHBr. Okay, this is the thing. Plus KOH is formed. Okay, aqueous KOH is formed. I'm sorry, aqueous KOH is not formed. It's reacted with aqueous KOH, and after the reaction with aqueous KOH, I hope you know the reaction. In case of aqueous KOH, like the bromine atom removes, it gets released, and OH ion reacts with CH group. Okay, so here this bond CH bond Br CH bond bromine breaks. Bromine acquires negative charge, and CH group CH the carbon has positive charge. So and in cases of KOH, potassium acquires positive and OH becomes negative. So negative OH reacts with the positive carbon and forms CHOH, and KBr is also formed. I'll also write it here. So you guys might be thinking that why haven't I written, right? So plus KBr is also formed. Okay, so why haven't I written KBr? Because it's a side product, it's not a main product. Our main aim was to convert propanoic acid to lactic acid and not form KBr. Okay, our target was to form propanoic acid to go to lactic acid. We have reached there, so that's why I haven't written. But for the sake of your answer, you can write this answer, it becomes more perfect. Okay, so propanoic acid on Hell-Vollard-Zelensky reaction forms this compound. Then treatment with so on as so like after you practice a lot these conversions, like you'll get to understand the rhythm of these things. Okay, so till you get here, okay, till you get here, you will get to know that like you yourself can predict the next step. Okay, so what will be the next step? We have already reached there. Okay, and after knowing the formula of lactic acid, you know that this bromine group should be replaced with OH group and the work is done. So how to replace this bromine group with OH group? Treat it with alcoholic KOH, aqueous KOH. So on treatment with aqueous KOH, this bromine group will be replaced with hydroxyl group. Okay, OH group. So and this lactic acid will be formed. Okay, so our aim was to convert propanoic acid to lactic acid, and we have converted it. Okay, this is the thing. So just go through the things. I hope the things will be clear, and do contact us through our YouTube channel, through the comment section. And if you are like if you want a self like 1:1 doubt clearing session, and we are also available for that. So just like go to our website and book a slot for you guys. And like we have our app upcoming, so just go through that app, like download it from Play Store. Like you'd really like the app. We have like made it student friendly as much as possible. So happy learning. Thank you.